So we examine the case of a flat square sheet of mass large M with a mass small m placed on it in two separate positions. Mass small m is placed on the corner of the sheet in the first case, and small m is placed at the center of the sheet in the second case. And the ratio of the universal gravitational potential energies of the small mass m in the two systems. So we know Newton's law of universal gravitation potential energy is negative gmm over r. However, the issue is that this is not two point masses, only one of them is a point mass, the other is a spread of mass, which is too close to approximate as a point mass. So we have to integrate over the course of the sheet. Instead of saying large m, we're going to call each individual point a small dm, where dm is given by the average density of the sheet, the surface density, sigma times dA, which is sigma times dx dy, which gives us our integral operators. Sigma is also equal to m over the mass over the area, which allows us to plug in a moment. So each distance where each different dm is given by the distance formula, Pythagorean theorem, square root of x squared plus y squared, which means that we are able to put that into our r and say that the potential energy is negative gmm over L squared, integral from 0 to L, integral of 0 to L, of 1 over the square root of x squared plus y squared dx dy. This is really hard to solve in Cartesian, but is trivial, a very famous integral actually in polar. We just convert to polar. X squared is equal to r squared cosine squared. Y squared is equal to r squared sine squared. So when we factor these out, we get r squared of 1 because it's cosine plus sine squared because it's x squared plus y squared, square root. So we get r on the bottom because all of this is happening on the bottom. And then the Jacobian is r dr d theta. So it's 1 over r times r, which just gives us dr d theta. And so we have a massive reduction in what we're solving. We have dr d theta here, but now we need to find the bounds, okay? The bounds are given by looking at the trig. We have, for anything that is below this symmetrical line, we have r is equal to the cosine of L. We have r times the cosine of the theta, hypotenuse times the cosine of the theta, gives us the horizontal component L, 4, 0 to pi on 4. So that means r is equal to L over cosine theta, or L secant theta. Up here we have L over sine theta, or L cosecant theta. However, this is gravitational potential, and this is symmetrical, the same amount of mass at the same distance to the point. We know it's going to be the same. We also can justify this by looking at the secant cosecant graphs and seeing that they are translationally shifted, which means the area under their graph are also going to be the same. So we know that whatever we get is just going to be 2 times this instead of having to evaluate a whole separate interval. So upon doing this, we integrate dr d theta, L secant theta stays in to be integrated in a second, L comes out, we get one of these L's to cancel, and now we have negative gmm over L of the integral of secant theta. The integral of secant theta is ln secant theta plus tangent theta, so we have ln secant theta plus tangent theta evaluated from 0 to pi over 4, and so we get secant of pi over 4 is 1 over cosine of pi over 4, which means root 1 over root 2 on 2, so 2 on root 2. 2 on root 2. So we have ln of 2 on root 2 plus tangent of pi on 4 is famously 1. So we get ln 2 on root 2 plus 1 times 2. It's times 2 because we need to do this twice, okay? So that is for, all the constants are here, negative gmm over L, but this is the scaling factor of potential gravity corner, okay? So now we want to do the same thing for the center, but we're going to leverage heavy symmetry here, okay? We're going to say that now this mass is placed at the center of here, and we're just looking at one quadrant. So in a way, this is the same as saying everything is the same. Nothing has changed, except now each of the sides is L on 2. And since we're looking at one quadrant, now we're still going to do this one thing, right? We're still going to have the half of a quadrant, which means whatever we get for this answer, we're going to multiply by 8, because it's 1, 2, 3, 4, 5, 6, 7, 8 potentials around this central point mass. There's more going around, okay? If we do the same thing, everything stays the same, except now instead of L secant theta, we have L on 2 secant theta. And so down here, this, instead of coming as L, comes out as L over 2. So now we have times L over 2. So we have over 2L. The L still cancels with this one squared. It's L over 2. Everything else stays the same. It's still square root 2 on root 2. So now we have ln of 2 on root 2 plus 1 times 1 over 2, which came from this L over 2 factor, times 8, which means that now we have UG center, or 4 total, okay? So all these constants are still here, GMM over L, all these here. So we put that on top, put it on the bottom, those are gonna cancel out, but the scaling factors do not, which means the only thing that stays is 2 on 4, meaning that the total ratio of UG corner to UG center is equal to 2 on 4 is equal to 1